So hi guys, so in this lecture as well we'll be continuing on seeing Schrodinger wave equation. So let's get started. So with the first note that phi is a electron wave in an atom, and electron wave in an orbital of an atom is can also be called as phi. So just some definition on phi, that it is a phi is an electron wave in an atom. Okay, and electron, it can also be secondly called or termed as electron wave in an orbital of an atom. Electron wave in an orbital of an atom. Okay, so with both the things we can tell something about phi. Okay, so let's see this, that I hope you guys remember that we discussed about polar coordinates and Cartesian coordinates in the previous lecture, so we'll be just using them. So let's say this is the x-axis, z-axis and y-axis, and we have electrons something here. Okay, so electrons position can be termed as x, y and z, and by how do we call it? By projecting electron in x, y and z axis. I'm just representing z axis with a dotted line. Let's make a full line here. Okay, so drawing perpendicular on all the axes will determine the coordinates or the position in Cartesian form, and then we can also have the position as, or rather in the polar form we can also represent them in terms of r, theta and phi. Okay, so the in polar form we can represent, rather let's draw it with a different pen. So in polar form, this is the distance r, angle with y-axis is termed as theta, and angle with x-axis on the projection here of the particle with x and y axis, or rather with x and y axis. Suppose this was the position, so this is the angle phi. Okay, so this was r, theta, phi as the polar coordinates which we mentioned in the previous lecture, and x, y, z as the Cartesian coordinates. Okay, so let's discuss on the angular and radial parts of hydrogen atom wave function. So before going into that, so let me write that x is equal to nothing but r sin theta and cos phi. Y would be nothing but r sin theta sin phi. Okay, and z would be nothing but r cos theta. Okay, so phi, let me define. I think in few seconds back I might have termed this angle theta with the y-axis, but it is not with the y-axis. This is actually with the z-axis. Okay, so for better understanding, let us do some changes here so that you get to understand this better. So imagine that this electron is in air somewhere, and this was the ground plane. Okay, so let me mark this as y-axis and this as z-axis, which is coming out of the plane. Okay, so you can imagine that x and y are the ground, okay, and z axis is in the air. Okay, so now what we can actually write here, that this electron is in air and it is making an angle of theta with the z axis which is in the air, and when we project this electron on the ground, it makes an angle phi with the x axis. Okay, so now if we project the position of electron, which is xyz, or rather the distance of from origin to electron would be in polar coordinates is r. So when we project this distance onto z axis, it would be nothing but r cos theta, which is z. Okay, and when we project this electron on the ground, it would be at this position, it would be nothing but r sin theta. Okay, so now this r sin theta would be nothing but this distance. Okay, and this distance would be nothing but r cos theta. Okay, so this r sin theta when projected on x axis would be r sin theta cos of phi, and on y axis when you project it, it would be r sin theta sin of phi. I hope by now it should be clear. Okay, so now let's discuss the angular and radial parts of hydrogen atom wave function. Okay, so the angular part is, as we have discussed in the previous lecture, it is a l comma m dependent on theta and phi. So for s orbital, angular part would be, we are writing as, and that would be 1 by 4 pi of, rather root of 1 by 4 pi, and for p orbital, a of p would be, or px rather, would be 3 upon 4 pi 1 by 2, that's the power, and sin theta cos phi py would be, angular part of py would be again 3 by 4 pi root, and then sin theta sin phi, and then apz would be 3 upon 4 pi 1 by 2 cos theta. Okay, so for now don't worry about how these terms are coming. These terms are coming by a lot of complex calculations done by Schrodinger. We are directly utilizing and consuming the terms, okay, for remembering sake. So for the radial part, we would be having r n comma l r. Okay, as we discussed in the previous lecture, radial part would be this and angular part was this. Okay, so for radial part, r for 1s would be 2z upon a naught 3 by 2 e to the power minus sigma by 2. R for 2s would be 1 by 2 root 2 z upon a naught to the power 3 by 2 2 minus sigma multiplied by int e raised to the power sigma by 2 minus sigma by 2, and R for 2p would be 1 by 2 root 6 z by a naught to the power 3 by 2 sigma multiplied with e to the power minus sigma by 2. Okay, next we see R for 3s would be 1 upon 9 root 3 z upon a naught to the power 3 by 2 multiplied with 6 minus 6 sigma plus sigma square multiplied with e to the power minus sigma by 2. So all these terms, don't be getting intimidated by all these terms. You just read the notes twice and thrice. All these values should be you'll get to know and remember these values quickly, or even better, practice some of the questions on the same and you will be able to memorize it. 3p would be 1 upon 9 root 6 z upon a naught to the power again 3 by 2 and 4 minus sigma into e to the power minus sigma by 2. And finally r for 3d would be 1 upon 9 root 30 z by a naught to the power 3 by 2 multiplied with sigma square multiplied with e to the power minus sigma by 2. Okay, so now let's define. Sigma is 2zr to zr upon na naught, where n is the principal quantum number and a naught is h square upon 4 pi square m k e square which is 0.529 angstrom for hydrogen atom. Okay, so with this we come to the end of this lecture. In the next lecture we'll be continuing on our discussion on Schrodinger wave equation.